Welcome to standard enthalpies of formation. So the standard enthalpy of formation, delta HF naught, so the delta means change in, H is enthalpy, F is formation, the naught there means standard. We're fixing this change in formation enthalpy to standard conditions. That's what the naught is. So delta HF naught is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all the elements in their standard state. So we're making our compound using elements in their standard states. Again, our degree symbol here on a thermodynamic function indicates that the process has been carried out under standard conditions, which means it's a certain set of things. In general, it means the temperature is a certain value. Usually we mean 25 degrees C. The pressure is 1 atmosphere or 1 bar, depending on how exactly we're defining it. And a few other things. So the standard state of a substance is a precisely defined reference state. So this reference state is important because we have no way of measuring the enthalpy. All we can do is measuring a change in enthalpy. So we measure changes in enthalpy. We can't measure what the enthalpy is itself, but we can measure changes as we change from one substance to another, one form to another. If we boil water, let's say, or condense it, we can measure that enthalpy change, but we can't measure what the enthalpy of the water is as a liquid in the liquid state or in the gas state. We don't know what it is. We have some reference frame relative to some value that we don't know what it is. So conventional definitions of standard states for a compound is the standard state of a gaseous substance is a pressure of exactly 1 atmosphere. For a pure substance in a condensed state, so a liquid or solid, the standard state is the pure liquid or pure solid. For a substance present in a solution, our standard state is the concentration of exactly 1 mole per liter of solution. For an element, the standard state is the form which the element exists, in which the element exists under conditions of 1 atmosphere and 25 degrees Celsius. So let's examine the oxidation of N2 by O2 again, like in the last video. We have now, note that I've changed the coefficient here on nitrogen. We have half of an N2 molecule, which means that we're only using 1 nitrogen atom, plus O2 gives us NO2. So I'm doing this to give us 1 molecule of NO2. Right? That's why I've put this half in there. So here we have delta HF naught is equal to 34 kilojoules per mole. Note that in the last video, I had a 1 here, a 2 there, and a 2 here. I basically doubled all of those, and so we needed to double the enthalpy. It was 68 kilojoules. So note that in this case, the reactants are elements in their standard states. We have nitrogen in its gas phase, oxygen in its gas phase, and only 1 mole of product has been formed. So we've only made 1 mole of product here. That's why this value is half as much. And note that I'm saying per mole. So now I can say that because we're making 1 mole of NO2 and we get out 34 kilojoules of energy, that means that for every mole that of NO2 we create in this way, we'll get, or rather we have to put in 34 kilojoules of energy. So now it doesn't matter whether we actually make 1 mole or not. We just multiply by however many moles we made, and we can figure out how much energy we have to put in to get that process to go. So enthalpies of formation are always given in terms of 1 mole of the product, so the compound being formed. And the formation of methanol looks something like this. So we have carbon in its standard state, which is solid. Carbon standard state would be graphite at 1 atmosphere and 25 degrees C, plus hydrogen in its gaseous state. We need 2 hydrogen molecules, plus half of an O2 molecule, gives us methanol. So CH3OH is methanol. Its standard state is liquid. So at 25 degrees C, it's a liquid. So the enthalpy of formation here. Standard enthalpy of formation is minus 239 kilojoules per mole. This minus means that we get energy out. So if we start out with our elements in their standard states and we make methanol, we get energy out, which means methanol should be a stable compound. In fact, it is. I can go into the stockroom and I have some methanol there. So suppose we want to calculate the enthalpy change for the combustion of methane. So we start out with CH4, and we add some oxygen gas, and we make some CO2 and water, and we'll get some energy out. So using Hess's law, we can now separate this process into 4 separate processes. 2 that break the reactants into their constituent elements in their standard states, and 2 that form the products from their constituent elements in their standard states. So we're going to break apart the methane into its standard state. We're going to break apart the oxygen into its standard state, which means really we're not going to do anything. And then we're going to form the CO2 from its elements in its standard state, the carbon and oxygen in their standard states. And we're going to form the water from the hydrogen and oxygen in their standard states. So that's what we have here. So we have methane splitting apart into atomic carbon and hydrogen gas. We have to put in 75 kilojoules per mole to get that process to happen. We have oxygen going from oxygen gas to oxygen gas, which means essentially nothing is happening. That means that the delta H, the enthalpy change there, is 0. That's not terribly surprising. Note that we have to do that twice because we have 2 oxygen molecules involved here. And then we have our solid carbon that we took from up there, plus one of our oxygen molecules gives us carbon dioxide. We get out, so negative enthalpy here, negative 394 kilojoules per mole. And then we have this reaction occur twice. So H2 plus 1/2 of O2 gives us H2O, gives us some water, and the delta H there, the enthalpy change, is negative 286 kilojoules per mole. And so if you add up all of those reactions, take all of the reactants and put them on one side, take all of the products and put them on one side, and then cancel things that are on both sides, you end up with this reaction. CH4 plus 2O2 yields CO2 plus 2H2O. And we can then add up all of our enthalpy changes. So we take our 75 kilojoules per mole and double our 0 kilojoules per mole and our negative 394 kilojoules per mole and double our minus 286 kilojoules per mole. And that gives us a total of minus 891 kilojoules per mole. So this now means that our standard change, the enthalpy change for a reaction at standard state, can be calculated by something that looks like this. So here we have delta H reaction naught. So this is the enthalpy change for our reaction at standard state, is equal to the sum. That's what this capital sigma stands for, the sum of NP delta H F naught of our products. So NP here and the NR over here are the moles of each product and reactant respectively. So we have the number of moles of each of the product times the enthalpy change of formation of that product, summed over all of the products, minus a similar sum over all of the reactants, so the number of moles of that reactant multiplied by the enthalpy change of formation of that reactant, summed over all of the reactants. And that whole sum gives us the enthalpy change for our reaction. So note that we don't really need to include an element in its elemental state in the calculation because the enthalpy of formation for the element is 0, because you're starting out and ending with the same substance and in the same state. So you don't really have any change going on. So that was standard enthalpies of formation.